In the next talk.
Ever seen a subdivision full of abandoned?
Okay. So now we are going to have Anissa Tapper, Gillian Durand, Maddie Ross from St. Kate's, and the title of the presentation it's not correct. The correct one is observing atmospheric change caused by solar eclipses. So please, now it's your turn.
Hi everyone, my name is Maddie Ross, and I'm a member of the St. Kate's High Altitude Ballooning Team, along with Jillian and Anissa. And Jillian and I will be presenting on some atmospheric changes caused by solar eclipses. This is the abstract for our research, and this presentation will focus on specific parts of our abstract, as well as the analysis of the respective data and how we collect data. If you were able to attend our first talk, you'll notice both some similarities and differences to our other project. To collect data during eclipses, we use high-altitude weather balloons filled with hydrogen or helium gas, and we send various sensors and trackers into the stratosphere via these high-altitude balloons. Figure 1 shows a weather balloon upon its ascent. The large white circle is the balloon, attached to the balloon is the payload, and directly under the balloon is a parachute with the tracking device. The contents of the white box are identified by the arrow and shown in Figure 2. This box consists of Geiger-Müller tubes or GM tubes that count high-energy particles in the atmosphere, a pressure sensor, a temperature sensor, an Arduino board that is used to read signals from the sensors, a heater to ensure functionality of the materials as they travel through near space conditions, and a GoPro camera to provide visual data. Under the white box is a black box that consists of additional sensors. Below those two boxes are some other tracking devices that use both radio signals and GPS. To conduct our research, we send the balloons with their attached payloads into Earth's atmosphere. The stratosphere and tropopause are identified in Figure 3 by the blue arrows, and we primarily collect data in the stratosphere. The stratosphere is a layer of Earth's atmosphere from approximately 14.5 to 50 kilometers above the Earth's surface. Our balloons reach a maximum altitude around 30 kilometers. Upon their ascent, our balloons travel through the troposphere, which is the lowest layer of Earth's atmosphere. And between the troposphere and the stratosphere, our balloons pass through the tropopause, which is important to note because it is the boundary between the decreasing temperature of the troposphere and the increasing temperature of the stratosphere. Temperatures at the tropopause can reach negative 75 degrees Celsius. Figure 4 depicts a sample high-altitude balloon flight. So after the balloon is filled with the lift gas, it descends into the troposphere, tropopause, and eventually stratosphere. While the balloon is in the stratosphere, it passes through the Regner-Pfotzer maximum, or RP max. This is the highest level of radiation and peak level of ion production. The balloon bursts when it reaches a high enough altitude and descends via its parachute. When it reaches Earth's surface, we recover the balloon and attach payload to gather the collected data. On the x-axis of this figure, you will notice the time after this particular balloon was launched. On the y-axis is radiation exposure measured in micrograys. Micrograys are used when radiation is measured in relation to its effect on the human body. For our research, we measure radiation in counts of high-energy particles, but for the purpose of this figure, these two measurements are directly proportional. We will use high-altitude balloon flights like the one described in Figure 4 to collect data during different types of eclipses.
One type of solar eclipse our team will be investigating is an annular solar eclipse. An annular solar eclipse occurs when the moon passes between the Earth and the sun. The moon is not able to completely block the sun's view, so we end up with a ring of light appearing around the moon. This ring of light occurs because the moon is further from the Earth than usual. We will be observing the 2023 annular solar eclipse. Another type of solar eclipse we will be investigating is a total solar eclipse. Much like an annular eclipse, during a total solar eclipse, the moon passes between the Earth and the sun. However, during a total solar eclipse, the moon completely blocks the view of the sun because it is much closer to the Earth. We will be observing the 2024 total solar eclipse. This table highlights information about the upcoming annular and total solar eclipses. On October 14th of 2023, the annular solar eclipse will be viewed in San Antonio, Texas. And on April 8th of 2024, the total solar eclipse will be viewed in Indianapolis, Indiana. Here we also noted the times in which each eclipse will occur in their respective time zones. The maximum time tells us the period in which the maximum coverage will occur, and the peak tells us when the moon is at the greatest coverage over the sun. The annular will give 90.16% coverage, and the total solar eclipse will give 100% coverage. More information about these two eclipses and our goals for them will be mentioned in our future plans section. So here are two visuals of the contact phases of both eclipses to show how the moon will progress in front and past the sun's view. Figure 7 shows the annular solar eclipses contact phases, while figure 8 shows the total solar eclipses contact phases. As we established, these two solar eclipses create different amounts of light, and because of this, we can observe different shadows created by them. There are 3 specific shadows that are created during these eclipses. These shadows will be discussed with their respective solar eclipse. During an annular solar eclipse, we have the penumbra and antumbra. The penumbra is a shadow that surrounds the central shadow and is seen in locations that are not in the path of maximum coverage. The antumbra only occurs during an annular solar eclipse within the path of maximum coverage. This is the darkest shadow created during an annular eclipse and is different from an umbra because it crosses over at some point along the shadow's path. During a total solar eclipse, we can see a penumbra as well as an umbra. An umbra is created by the moon obstructing the light's view and is the darkest type of shadow. Like an antumbra, the umbra can only be seen in the path of maximum coverage. So these are the path maps for both the annular in figure 11 and the total in figure 12 solar eclipses. The red line on the annular solar eclipse and the blue line on the total solar eclipse depict the paths of maximum coverage. And then these maps provide a better example of how the penumbra and antumbra of the annular solar eclipse in figure 13 and the penumbra and umbra of the total solar eclipse in figure 14 will move across the Earth. The darker spots in the middle of the large shadows are the antumbra and the umbra of their respective solar eclipses.
During solar eclipses, our research includes temperature measurements. The temperature measurements of our balloon flights are influenced by thermal wakes. A thermal wake occurs when a high-altitude balloon changes the atmospheric temperature of the surrounding air. During daytime flights, the air below the balloon is warmer than the surrounding air as a result of solar radiation. During nighttime flights, the air below the balloon is cooler than the surrounding air due to the cooling of the lift gas. During daytime flights, there is still cooling of the lift gas, but the warming as a result of solar radiation dominates, making the overall temperature below the balloon still warmer than the surrounding air during the day. Depending on the angle of the sun and the time of the balloon flight, the temperature profiles below the balloons can be symmetrical or asymmetrical, as shown in figure 15. The shadow formed during a solar eclipse creates a moving region where solar radiation is reduced during the day, as seen in figures 16 and 17. The balloon team hypothesized that the radiation cooling throughout the path of the eclipse would affect the temperature measurements, especially in the stratosphere. As a result of this cooling, it was predicted that the daytime thermal wake profiles measured under high-altitude balloons during the eclipse would be similar to the nighttime thermal wake profiles as a result of radiation reduction during the eclipse. The data from the temperature measurement showed that this was not the case, and that the thermal wake during a solar eclipse is unique in that it is different from both daytime and nighttime flights. Figure 18 shows the temperature data that we collected during various balloon flights. Flight 4N, the red flight, was a night flight. Flights 13D, 14D, 15D, and 16D were day flights, flown in their respective order, represented by the brown, gray, blue, and green lines. Flight 1E was the first eclipse flight, represented by the yellow line, and Flight 2E was the second eclipse flight, represented by the purple line. The day flights reached warmer temperatures as a result of solar radiation, while the night flights reached cooler temperatures. The eclipse flights primarily reached temperatures closer to the night flight as a result of the reduced radiation during the eclipse. In figure 18, you can see that the yellow and purple lines are somewhat in between the red line and the other colored lines, but are closer to the red line. However, it is important to note that the second eclipse flight temperature measurements start to drift back toward the daytime temperature measurements because the balloon was in the air post-totality. This is shown by the purple line representing Flight 2E, reaching values closer to the brown, gray, blue, and green day flights.
In addition to temperature measurements, we have previously flown and are continuing to fly GM tubes to take radiation measurements. GM tubes are ionization detectors, meaning they measure the charge produced during interactions between the detector and a radiation source. In figure 19, you can see an image of how the GM tubes are placed within our payloads. Figure 20 shows how the interactions occur and the overall mechanisms behind GM tube measurements. If a certain number of electrons are present within the gas, a pulse will occur. The pulse height is the same for every event, and no information about the energy created is produced. The electrons are attracted to the central wire. An electrical signal is generated from the central wire when there is a high enough charge. This signifies an amount of high energy particles.
During our planned 2023 and 2024 Eclipse flights, we are looking to collect additional information about high-energy particles by flying silicon photomultipliers, or SIPMs, to identify the presence of specific charged particles such as muons. SIPMs are a good candidate for high-altitude ballooning research because they are suitable for high-speed distance measurements. A SIPM consists of an array of solid-state light-activated pixels and can be seen in the circle in Figure 21. Each array in the SIPMs we plan to fly consists of 10,000 pixels. Light will only interact with one pixel at a time, and when a pixel is activated, it will send a signal that causes the energy to change. More specifically, when a photon hits the pixel array, an electron and an electron gap pair will move through the SIPM. The electron will separate from the electron gap and be pushed through the SIPM toward the negative electrode. As the electron moves to the right of Figure 22, it releases more and more electrons. Once it reaches the negative electrode, the signal is read out and a pulse occurs. We can count the exact number of photons that interact by the SIPM by the amplitude. From this data, we can determine the total energy of the pulse. When this is graphed, the counts can be identified, and the amount of photoelectron peaks can be converted to an actual energy and determine the energy of the specific event detected.
These are pictures of the actual detectors. These pictures are not to the same scale. The SIPM in Figure 23 is approximately able to fit into the mesh circle of the GM tube in Figure 24. The actual detector within the white circle, the actual detector of the SIPM is within the white circle in Figure 23. The specifications for each device are listed here. The SIPM weighs 76 grams, less than the GM tube, making it ideal for high altitude ballooning. Previously, our team performed 2 flights during a total solar eclipse in 2017, and we want to expand on this research. In 2023 and 2024, our team will be launching balloons in San Antonio, Texas, and Indianapolis, Indiana, to take the various measurements we listed throughout this presentation. We will be communicating and working with universities close to the launch sites. As our partners, they will help us complete the stratospheric research and provide resources such as a helium or hydrogen source that is vital to our flight. We are hopeful the additional measurements of SIPMs will allow us to conduct alpha particle research and quantify particle energy of each eclipse. The data we are planning to collect on temperature and high energy particles during future eclipses will be compared to past eclipse data and help to understand how measurements differ between annular and total solar eclipses. We would like to thank the U of M, Dr. Damos, and Minnesota Space Grant for this event. Does anyone have any questions?
I have a question. You guys want to be there to record these data, record the data. You guys will want to be there. You guys already have by 2023, 2024 graduated.
Mm-hmm.
So how is the dynamic here? You guys are learning, preparing things, and they have all the documentation to help the colleagues in future. Is this the plan?
Yeah, so we're planning to help our future team members as the years go on get ready for this event. And so once we do graduate, I know I personally will love to accompany them on this flight just to experience it.
And in addition to that, I'm actually a freshman this year, so I will still be on the team in 2024. And so I'll sort of help to ease that transition as well.
Oh, cool.
I have a question. I'm also, like I said before, like a freshman. So, is there a way I can join later on and be involved in the project by any chance?
Yeah, I think so. If you would just like to reach out to us or Eric, who is our advisor, that would be great.
That's cool.
Any other question? We still have some time left here. If you don't have more questions, I am going to stop recording and